We were talking about line integral, about conservative vector field, about potential. Let us summarize these results into the following sort of theorem. The following 7 statements are equivalent. In the sense, if one of them is true, then each of them is true, and vice versa. If one of them is false, the others are false as well. Curl of f is 0. This is the condition that the derivatives of first component with respect to second variable is equal to the derivative of the second component with respect to first, and so on. Curl is 0 in some open, simply connected set. Then the vector field has potential, is conservative, and so on and so on. The following equivalent statements are: the vector field f has potential. Again, everything is in some open, simply connected set. This is equivalent to f being equal to gradient of some function u, which is called potential. Note that there is a little arrow above f, meaning this is a vector, but there is no arrow above u. This is a scalar function, and its gradient is a vector function. And further, this is equivalent to the statement that this line integral of the vector field f along this curve C is path independent. That means that the value of the integral does not change if we change the details of the path of the journey with keeping the initial point and the end point the same. And this is equivalent to the statement that the line integral over a closed curve, that means a curve that returns back to the initial point, and this is denoted here by this little circle. Integral with this little circle stands for the line integral over a closed curve. Circle, square, triangle, curve like that. And this is equivalent to the statement that the line integral depends only on the end point of the curve C and the initial point of the curve C. Namely, it is equal to the potential at the end point minus potential value at the initial point, not depending on the remaining points of the curve. And this is just a sort of definition, such a field is called conservative vector field. Let me illustrate the connection between line integral over a curve C and line integral over a closed curve C. In particular, the implication 5 implies 4 might look surprising for someone. Because if we have some property that is true for all closed curves, how can we say that this implies something for other types of curves? Similarly, if you have some property that is true for all dogs, can we conclude that some property holds for all mammals? Perhaps not. But this time it is true. So if the vector field is equal to 0 for any closed curve, then we want to show that this implies that the integral is path independent. That means joining 2 points with curve C1 or with a curve C2, then integral over C1 is equal to integral over C2. Okay, let us introduce a loop, let's call it L as loop, which will be a curve that we take C1 from here to here, and then we take minus C2, which is the curve C2 but traveled in the reversed orientation, and we concatenate these 2 curves. Because the end point of C1 is the initial point of minus C2. Well, this is now a closed curve, because C1 and C2 start at the same point and end at the same point. Then we know that the integral of some vector field, of any vector field, of any conservative vector field f over the curve L is equal to 0. But L is C1 concatenated with minus C2. But line integral over a concatenation of two curves can be written as sum of these two integrals. But now, traveling over C2 in the reverse order gives the opposite sign as traveling over C2 in the original order, in the original orientation. And we know that this is 0. That means integral over C1 is equal to integral over C2. So this is a very useful knowledge, because if you see that this condition is true, and if you see that the curve is closed, then you have the result. No more computation necessary.